I hide this. Oops. There we go. All right. Hey. Yep, perfect. Let's see. All right. Am I muted or I'm okay there? Oh, testing. Yeah. Okay. Great.
All right. Shall we get started?
Yeah.
Okay. Welcome everyone to the last seminar of the course. Today we are very excited to have Dr. Michael, the professor of the program at the Fred Hutch, and his research focuses on the development and application of statistical methods for the preservation of time through the clinical trials and continuous studies. He applies statistical expertise towards the omics sciences, Wu is also a member of the Fred Hutch SWOT Center, which helps design and analyze science. Other areas of interest include reproductive and birth outcomes, autoimmune disorders, cardiovascular, environmental health. Michael, we're pleased to have you. The floor is all yours.
All right. So thanks so much, Artie, for the introduction. I'm sorry that Ting couldn't be here today, mostly because she probably would have given a better introduction, but that's okay. Thanks nonetheless. Yeah, no, thank you. So for those of you who aren't required to be here, thank you for being here. For those of you who are required to be here, well, I'm still glad that you're here. And so today I'm going to talk about some of the work that we've been doing on batch effects correction within the context of microbiome profiling studies. I know last week Amy gave a fantastic presentation on things that are far more sophisticated and far more detailed than what I'm doing. And so relative to that, this is pretty crude, but nonetheless, it's, I think, still a step in the directions that we need to go. Oops, this not. I might be too, I think I need to click onto this screen then. Yeah. All right, so over the last decade or into a decade and a half, there's been tremendous progress in microbiome studies. And to date, we've found tons and tons of associations between the microbiome and all sorts of different types of exposures, everything from diet and exercise, all right, to drugs and behavioral things, as well as treatments. So whether or not you're on cancer immunotherapy or not, your entire microbiome profiles can shift. We've also found that the microbiome is related to all sorts of outcomes. And of course, you know, this includes things like diabetes, cancer, asthma, all sorts of different traits and diseases of interest. I put a little question mark there because the fact of the matter is for many of the studies that are ongoing, they're cross-sectional. And so it's actually difficult to ascertain whether it's the microbiota driving the outcome or this disease, or that these shifts are sort of resulting from changes in health status. But regardless, the associations hold and have been pretty robustly identified in the sense that we're confident that the microbiome is related to these entities. So let's talk about a traditional microbiome study, maybe from around 10 years ago. Typically, you get a mouse, healthy, happy mouse. Then you get a very sad, unhappy mouse over here. You collect poo from each of them. You can tell that this is happy poo because when my poo is happy, it's also rainbow. And of course, when your poo is frowning at you, you know that it's been a really bad day. Okay? And so you take these, you process your specimens, and you do a comparison. All right? So traditional experiments. You had relatively simple questions and relatively simple designs. You got a handful of rats here, you got a handful of rats here. You fed them their own body mass in NutraSweet. And then you're like, hey, golly, gee, there is a big difference here. And so when you feed something its own body mass in anything, especially NutraSweet, you find that there are really, really big effects. So a handful of rats, a handful of mice was enough to find things as potentially interesting here. So there were relatively modest sample sizes at the very beginning. The problem, of course, is mice are not the same as people, no matter what some people seem to think. The reality is, if mice were the same as people, we would have cured cancer about 30 times over. We would have addressed every single complex disease that is out there. But mice are not people. What's the problem? Well, people are way more complicated. There's a lot more heterogeneity in terms of human beings. One of the major reasons is you're not allowed to lock people up in cages, all right? It's just frowned upon in this country for some reason, all right? Not even faculty. You're not even allowed to lock senior faculty up there. Trust me, I asked them and they said, no, not allowed, all right? So the issue here then is that we find that for human studies, many individual findings actually replicate quite poorly, particularly implication of individual microbial taxa. That's the unit of analysis here. And some of what we find is that here with humans in population-based studies, oftentimes effect sizes are much more modest. You're no longer ending up with huge, huge effects because, well, you fed something its own body mass in something. And so one way to get around this is to use larger sample sizes. And in fact, that is what is needed. The alternative is that you find some individuals who are willing to be locked in cages, perhaps junior faculty, and that might be allowed, all right? It's not entirely clear. Yeah. So, all right, assuming that we don't lock Kevin up in a cage, all right, let's see what we can do. Well, one thing is that we are now dealing with large-scale microbiome profiling studies where you now have much larger sample sizes. And so this offers a lot of opportunities in terms of allowing us to robustly and powerfully identify associations, as well as ask more sophisticated questions of the data over here. And by that, I mean looking at things such as effect modification, studying some degree of causality, and other types of things that you might be interested in beyond simple associations, all right? Also, with many of these studies, they're typically conducted within existing cohorts. And so there tends to be very, very rich metadata. All right, so that includes everything from exposures that these people have been subjected to, risk factors, outcomes, other omics, all sorts of strange and wonderful things that you might be interested in exploring. And so some examples of cohorts that have now collected microbiome samples include the cardia cohort, about 600 individuals, which was large at the time. The PIN is a new pregnancy cohort with about 1,200 people. Hispanic Community Health Study has 3,000. MEC has 6,000. NCI has 10,000. And I was very, very happy when I was talking to the NCI, and they were like, nurses now has at least 25,000, perhaps into the 100,000s of specimens. So there are now these huge, huge studies going on. So big sample size in statistics, bigger is better, right? We always tend to think that way. But the problem is actually that being bigger also leads to some challenges. One set of issues are challenges that are inherent to the large sample sizes, all right? Because now you have a lot more samples, you have to process a lot more samples, batching of samples is now inevitable, all right? You're not gonna be able to run everybody on the same sequencer at the same time. You now have to deal with the fact that some of these are run over time and perhaps on different machines by different individuals. So batch effects become a real problem. At the same time, all right, there are also challenges that arise from new opportunities. One of the ones that I'll be talking about today is a particular approach for implication of individual taxa in relation to an outcome of or predictor of interest. But other issues now, you are able to do things like effect modification. You're able to do things like causality with much larger sample sizes. And so how to do that optimally within the context of the microbiome is not always entirely clear. All right, but we're gonna focus on just these two relatively straightforward ideas. One is batch effects, and the other one is how do we robustly implicate individual taxa. So the first part of my presentation is going to be about conquering batch effects and microbiome data with Conquer, which is the name of our approach. I wasn't sure if it should be called Conquer or Concur, so naturally I went to a conference and I asked the audience. They tend to prefer Conquer, so there we go. I was like, you can either conquer batch effects or you can get data from different batches to concur, but I don't know. They had strong opinions about this. Partially, I think, because one of the current most popular approaches for batch effects is called combat. And so conquer and combat are both sort of these aggressive words that I guess people sort of like. All right, so what are batch effects? By definition, batch effects refer to systematic variability in your data that arises through some degree of differential processing or handling. And so this can come from using different instruments, all right? It can be machine drift over time. It can be things collected at different locations, different sites, slightly different protocols. It can even be the batch of reagents that you use or the technician who is processing the samples. All of these types of things introduce variability into your data, and we oftentimes refer to as batching in this case. The issue with batches is that from the perspective of implicating individual taxa and overall associations, they can paradoxically lead to both false positives and false negatives. All right, false positives because you have some degree of unbalance in your study with regard to variables of interest, and false negatives because there's simply additional variability in your data that, if you don't model appropriately, can, well, make your standard errors bigger than necessary, right? Now, batch effects are not unique to microbiome data. In fact, they are ubiquitous across virtually all high-dimensional data types, everything from sort of germline sequencing, tumor sequencing, single-cell gene expression, proteomics. They are almost always there, all right? And so within the context of dealing with batches, all right, we typically refer to this as batch correction, and there's two major strategies for dealing with it. The first one is what I refer to as batch removal. The idea behind batch removal is you take your data and you basically scrub, to the best of your ability, the batch variable out of there, all right? So basically you remove the batch effect, and afterwards you have a single, quote unquote, cleaned data set that you can do anything you want with, right? The other approach is to do batch adjustment. Typically, this occurs within the context of association analysis, where you try to adjust for these additional batch variables somehow, or use some stratification, do some other approaches, but it's typically analysis dependent, and it's really contextually dependent. Whereas the first one is, at least in theory, supposed to scrub your batch effects out of there such that you can do whatever you want with the data, right? So here's an example of a study that was run in batches. So this is the Cardia study. So Cardia is a very old study looking at it's a very old longitudinal study on risk factors of cardiovascular disease. The microbiome data were collected at their year 30 follow-up, which was in 2015 to 16. And they have all sorts of covariates related to CVD, blood pressure, all sorts of demographics, and other things that we might be interested in. And so these are the data. This is called a principal coordinate analysis plot. In statistics, we also call it multidimensional scaling. And so this is basically, which you can view for students as a nonlinear version of principal component analysis. And so what each point here represents a separate sample over here, each of these dots. Each of the colors and numbers correspond to a different batch. All right, so these were processed across 6 different runs of the sequencers. And over here, the squares sit right where the centroids are. And so this is using one scale, Bray-Curtis. This is on a Euclidean distance on the CLR scale called Atchison distance as well. And basically, you can see that overall, you see that there's some degree of spread over here across different batches. In fact, you look at number 2 over here, and it's basically not overlapping with any of the other guys. A reassuring thing, however, is that if you actually look at the shape of each of these guys, they're actually fairly similar in this case over here. So it says that perhaps some relative things look okay, but if you want to combine across all of these different batches, all right, you have to do something at least, right? So batch correction for microbiome data. The first thing we said was, can we just borrow approaches from other omics data? Well, by far the most popular approach for batch correction is something called Combat, developed by my good friend Evan Johnson in his first year of graduate school. It was his idea, not his advisors, and it was actually a really, really cute approach, which is relatively straightforward. The idea is very simple. Let YIK be the kth microbe measured on the ith individual. And then what you do is you regress it on a bunch of covariates of interest, as well as basically indicators for batch. And effectively, you take the residuals as your, you take the residuals, add back on covariates that you know about, and that is basically the corrected value. Now, their actual procedure is slightly more complicated, but as sample size goes up, this is basically what it will converge to. Very, very simple, just linear regression. All right, nothing terribly complicated over here. There are generalizations for count data, all right? But one of the challenges here is that they make very, very strong assumptions regarding the distributions. So they tend to focus primarily on negative binomial distributions, which don't always work out particularly well, particularly for microbiome data, where we have very, very ugly zero-inflated, sometimes over-dispersed count data, sometimes under-dispersed, all sorts of terrible things going on with these data. There are a few approaches that have been developed for microbiome data, but they tend to have some degree of limitations, either by requiring specific types of controls, samples, or spike-ins, or they do focus on batch adjustment rather than batch removal, which is to say they only focus on the association step. And in many cases, that may be sufficient. But if I'm also interested in things like data visualization or exploration of other things, then this may not be an ideal strategy over here. Okay, so hence our proposed approach, which we call Conquer. So here's the punchline of the talk. These are the Cardia data before correction. It's exactly what we saw before. This is what we see after correction, right? So before, everything is, you see, pretty different. After, everything is pretty much on top of each other. The spread is pretty similar over here. It's not perfect in the sense that you don't want everything to be exactly the same, but it's much, much closer in this case, all right? And this is true both on using this Bragg-Curtis dissimilarity scale as well as the CLR Euclidean scale. All right, so here's the idea behind Conquer. It stands for conditional quantile regression. The idea is very, very simple. You take a single taxon, you estimate the distribution of the taxon given covariates and batch, and then you just simply remove the batch variable. It behaves exactly like Combat, all right? Very, very straightforward. Operationally, all right, what we do is, for estimating the distribution, we use quantile regression across a fine grid of quantiles in this case. Right? The idea is borrowed from Combat-seq, but whereas Combat-seq makes a very strong assumption of a negative binomial model, which we don't think fits the data very well, all right, we're using a quantile approach which makes no distributional assumptions in this case. All right? And so overall, we better estimate quantile functions by handling zero inflation and over dispersion in this case. In order to deal with the zero inflation, we use a two-part model it's quantile based for the non-zero parts, such that it's robust to complex distributions, and it also allows you to correct for higher order effects in the distribution. You're no longer constrained to just simple means and variances. We can, in principle, correct for other things that are not well characterized by means in just the mean and variance. So here's our actual model. This is a two-part quantile regression model. And so for the probability that it is equal to 0 or not, we just use a simple logistic regression. Depends on a bunch of covariates as well as batch over here. For the positive part, we use a conditional quantile model. It's conditioned on the fact that it is greater than 0 in this case. And it again depends on a bunch of covariates, Z, and also batch over here. Now, W over here is a slightly jittered version of the data. You have to jitter it a little bit in order for the fidelity of the model. I mean, it's a quantile model for discrete data, and this is pretty standard in this case. So again, all we're doing, simple regression model, logistic for whether it's 0, non-zero, and for the other part, or the continuous part, we're using a quantile regression approach, but it has to be conditioned over here. So that is something that makes it a little bit messier over here. So here's a correction procedure for each taxon. What we do is we fit the two-part quantile regression model. All right, there is some statistical messiness over there dealing with some change points and things like that, but I'm going to sweep that all underneath the rug for this pretty applied presentation. Then we estimate the original quantile function for each sample. So this is done on a taxon by taxon basis, a feature by feature basis, and we're going to estimate, all right, it's each sample's distribution now. All right, so it's for each sample and each subject. Then we estimate the corrected quantile function of each sample by removing the estimated batch effect. You have your model, you just take out your batch effect, all right, and you get very nice distribution over here. Then what we do is something called quantile matching. Basically, you look at your observation and you say, hey, this was at the 10th quantile of the original distribution. Then I go down to my corrected distribution and I find the 10th value, and that is now my corrected value. So to illustrate this, and then we do this for all taxa. So to illustrate this, what we do over here is, this is just a single sample, and this is its estimated its estimated distribution over here. All right. So this is quantile level against quantile of taxon count, and this is the distribution that the original distribution. This is what we call the batch-free distribution after you've removed the effects. And so what we do, we say, hey, this guy started off at a value of 1500. This was at the 80th percentile. And so then you come down to the corrected one, 80th percentile is over here. And so now the corrected value is about 700. Okay? So it's a very, very simple quantile matching approach. In fact, this is exactly the same as what most of the other approaches do. It's simply that they have a very nice parametric model. And so they don't need to do the quantile approach, whereas we do. There is some degree of messiness over here. I'm not going to talk too much about the details, but because it's conditioned, you just have to be a little bit careful about it. We also have a change point problem between the last observation where something is 0 and the first time something is non-zero. And so what we do is we just interpolate the distributions over here. Okay, and I'm going to skip this. So, yeah. Yep. So we operate directly on the count data always. Yes, we start from the count data. The CLR was after we've corrected the counts, then we CLR transformed and calculated the Euclidean distance in that case. We have the raw counts. We don't do any correction. We have a version that also does corrections for read depth and things like that, but all of this is just the raw read counts over here. Yeah. Yes. All right. So the nice thing is actually by doing this approach, it actually does a pretty good job of normalizing read depth in this case. But that's an aside. But here's the overall approach. What you do, you give read counts for all samples. All right, and then we use a two-part model, logistic model for positive versus 0. And then over here, we use a quantile regression for the continuous component. And so basically then you have a couple of outputs. This is the conditional distribution estimation on this step. And so this is for the probability of being 0 or not. And then over here, and then here's the continuous part. And then after you remove the batch effect, then these are the corresponding probabilities. And here is the anticipated distribution for a single subject at a single taxon over here. And then following that, we do matching. So conceptually, relatively straightforward. Operationally, relatively straightforward as well. It does take a little bit of time to run, usually about a minute or two for a medium-sized data set, but it's not too bad. So the interesting thing here is that our approach can take values that are 0 and set them to something that is non-zero, all right, which was a little bit concerning, but seems to have worked out. It can also take values that are non-zero and correct them to 0, and also take values that are non-zero and correct them to something else that is non-zero in this case, all right? So all of these things are feasible within our approach and are done. And so this is just a single genus that we looked at in the Cardia data, and these are 3 different individuals in this case. So some people had their value corrected to 0, other people had their 0 value corrected to something positive, and some it just shifted the specific value over here. Yeah.
Just clarify, so like if we're looking at the Q hat zeros,
Yep.
I think if this is like the composition of the 2 stages, because like the
Yeah.
zeros are coming from the logistic part, not from the quantile part.
Yes.
But
Yes.
you put it back together, you then get the
Yes.
prediction.
Yes. And so that's where we have the issue that, and we just interpolate. Yeah, because I don't know what else is the right way to do it, but And it seems to work, at least. So, yeah. All right, so let's see how this approach actually works. So we have tons of simulation data, and of course, in simulations, everything always works out. If it doesn't, then, well, you should just go home. Because if you can't even do it with made up data, then with real data, it's gonna suck even more. So, all right, here we have about, after cleaning it up, we have about 380 taxa on 540 samples, which were measured across 6 batches. The key variable of interest in this case was systolic blood pressure, which is a continuous variable of interest, and other covariates that we chose to adjust for: age, gender, race in this case, as measured with these studies. Bear in mind, these are relatively old studies. Some of the definitions are old, but this is what they coded. And so here are the PCOA plots, so the principal coordinate analysis plots, before and after correction. So this is the original, this is just Bray-Curtis on the original scale, all right? This is Euclidean on the original, Euclidean distance on the original scale after CLR transform. This is what happens if you apply combat-seq. So it looks a little bit better, but you still see a fair bit of separation. On the Euclidean scale, it does a little bit better. And then this is what happens with Conquer. So it tends to at least make most of the batches look more similar in this sort of global visualization approach. So it's not a particularly formal analysis, but at least it's looking a lot better, right? These 6 batches, they're not really supposed to be very different. And so now they don't look as different globally. All right, well, so the issue then is, if I want to correct batch, I can just make all of my numbers the same across all batches. I take my hammer, all right, and I smash my data into little itty bitty pieces until there's no signal or anything left. It'll be batch free, all right? What I also care about is whether my signals of interest are preserved. So here are per MANOVA R squareds. You can think of it as a particular choice of multivariate R squared. And so this is the variability explained by batch, all right, in the original data. So it's about 10% over here. This is the amount of variability explained by systolic blood pressure in the original data, about 0.4%, all right? And so if you apply combat-seq, it takes this batch, the variability explained by batch down quite a bit, but not as much as if you apply Conquer. The nice thing, however, is that the variability explained by the variables of interest continues to be maintained in this case, right? And this is because we've actually incorporated it into our correction procedure, which does lead to some additional challenges, okay? So this is the per MANOVA R squared before and after correction. So I showed this to my collaborators. They're like, oh, wonderful. But you didn't do a random forest. Apparently, for all microbiome studies, you're sort of required to do random forests. I have no idea why, but my collaborator really wanted to do a random forest. And so this is basically telling you the exact same thing. All right, this is the RMSE from the original data for predicting systolic blood pressure. This is it after using combat-seq, and this is using Conquer. Again, it's just globally looking at how well it's doing predictions and associations. Nothing new. Take home from this, microbiome researchers love their random forests for no reason other than somebody did it once, and now everybody has to do it. Yeah?
What are you predicting, and what are you using to predict?
We're using the microbiome, in this case, to predict within sample, it's cross-validated, systolic blood pressure, which is a continuous, yeah. It doesn't work for predicting outside of my batches, which is why I thought this was a sort of stupid exercise, but they always want to see it. Yeah. We've not tried predicting batch. That is actually something that we're starting to work on going forward, where we're actually interested in understanding which bacterial taxa really suffer particularly from batch effects, and we're trying to characterize those guys. And so, at least we're trying to figure it out. I think it's going to have to do with GC content and other things like that. And then the nice thing about that is then you can actually do single sample normalizations if you're able to really tease apart what's going on there. But that's sort of very early days, and whether or not it pans out, no idea, which is why it's called research. So, all right. So this is one example here. Another example, mega-analysis. So this is data from the HIV reanalysis consortium. And so this study looked at aggregated data from different studies where all of the specimens were collected across studies with various protocols and designs. The idea is they wanted to combine this set of studies, all right? And so what we're gonna do is we're gonna treat each study as a separate batch and try and smush the data together, all right? For the record, this is an awful thing to do, but when your collaborators pay you, 10% effort to do it, you still have to kind of try over here. And so I have to be honest, it's much more challenging than a traditional batch correction where there are batches, but the differences are oftentimes fairly modest. And so here, what we have are pooled data. All right, we have 600 taxa measured on 572 individuals from 10 different studies. All right, so each of the 10 studies we treated as a batch. They range from 24 to 135 patients each. The key variable of interest, all right, in this case is HIV status. They wanted to understand which bacterial taxa are related to HIV status. They had covariates over here, age, BMI, and gender, where gender is actually a very complicated variable, which basically amounts to receptive anal intercourse, which is really the thing of interest in this case. You have a question? Okay, because you're pointing. And so, when you point, it's, no, I'm kidding. Junior faculty, they'll figure it out at some point. All right. So this is what happens with our data. These are our original data, and you can see huge differences across study, and that makes sense. These were totally separate studies, all right? And so this is on the using Bray Curtis, and so you see if you do combat seek, it does a little bit, it doesn't really do much. Conquer does seem to help. At least everybody is looking a little bit more similar, but it's still not perfect in this situation. You can see. All right, not everything overlaps exactly. These spreads are not entirely there, but it's way better than this guy over here. All right, so let's take a look at the Permanova R squared. So original variability explained by batch, which are different studies, 30% of the variability there, all right, in the microbiome. If you use combat seek, drops it to 20%. It's not bad. You look at Conquer, it drops it down to 1.2%. So that seems, hey, this is great. Until you look at the variability explained by HIV status, which is like 0.7% over here. So Conquer is not a perfect approach. It is not a panacea, all right? But we think it's a step towards the right direction for dealing with some of these things. And we've been lucky that at least a number of groups have been using this approach for better or for worse. One paper, which is totally wrong, who did it for worse. And I'm sort of embarrassed that they used our approach and then use it to justify the cancer microbiome, which doesn't exist. But nonetheless, it is what it is. All right, I can't keep other people from doing shitty analyses. Yes?
Do you think like if you look within the batches, like is the signal just weak? Or is it?
The signal is just weak in general over here.
It's not necessarily like, at least in this case, like the fault of conflict. Like,
it's not the fault of the methodology, but I'm just saying that the relative variability of batch, it still swamps the effect of signal. In fact, when we submitted this, the reviewer said, can you find a situation where batches effects are modest relative to the signal of interest? And we tried like 30 data sets and none of them was the signal. Even, at best, it was at the same order of magnitude as the batch effects. So, they tend to be really, really large. So, all right. So we also did another random forest, same story. These are the AUCs, okay, for predicting HIV status. It just cross-validated, and Conquer, it does better, but then that's also because that's as we already saw that over here. Nothing terribly interesting here. So a couple of remarks. In general, I think batch correction for microbiome data, it's an increasingly important problem as we try to combine studies. And as studies get bigger, you just have to do some degree of batching. All right, Conquer is a relatively general and robust approach over here for batch correction. It works on count data directly. It doesn't make any distributional assumptions. And it seems to be reasonably effective in removing batch effects while preserving signal overall. All right. There's some additional options that I didn't show. We have regularized versions of this. We can tune models across a range of different taxon prevalences. We can take read depth into account. All of these are in the software, but they're not terribly interesting for this presentation. There are limitations to Conquer. In fact, there are many limitations. First of all, it doesn't work that well on rare taxa. And this is simply going to be the case for any approach because you just don't have very much information there. I will say it doesn't do that badly, but when you have no information there, you can't do very much in general. It doesn't work very well if your batches are very, very small. Okay, you just don't have enough data to estimate the effects reasonably. The approach corrects each taxon individually. This is the case for virtually all batch correction approaches, but it only looks at one taxon at a time. It's never taking into consideration the correlation between any two taxa, which again seems to be the standard within most of genomics. I think I've seen people try to take into account some correlation networks in the batch corrections for gene expression, and they tend not to work that well on average. Okay. The other thing here is we are including the variable of interest in the model. So as we're doing the batch correction, we do include the variable of interest. So strictly speaking, this is double dipping, all right? We are using the variable twice. And so at least in theory, all right, our standard errors should be smaller than you would expect. In practice, through tons of simulations, we have not seen any type 1 error in inflation, but I note that this is a theoretical possibility, and there may be some situations where this is of concern. I simply have not run into it yet, and actually this is true for all batch correction procedures that are out there. They always include that in there, and so I haven't really seen it be an issue for combat or any other approach either. So, but it is at least conceptually still an issue here. All right, with that, I'm going to go very quickly through the second part of my presentation, which is talking about robust implication of individual taxa over here. And so this is a classical association analysis where I'm looking at the association between one taxa and an outcome, all right? And then we do this for each taxa one at a time. So this is a common analytic objective, all right? Identifying individual taxa. The usual approach is, well, you normalize, scale your data, and then for each feature, you assess the association with an outcome or other variable of interest. You control for multiple testing, and then you do whatever auxiliary analyses you might be interested in doing, whether it's some sort of pathway enrichment analysis or other types of unsupervised fun things there. All right. So in terms of association analysis approaches, I generally classify these into two different categories. All right. First, what you'll see is people just apply a classical statistical test, like, a t-test, a Wilcoxon test. Sometimes we call the Wilcoxon test LEFC just because people like giving it funky names, but they are basically classical statistical tests in this case. The other set of approaches that you can use are what we call loosely tailored approaches over here, where they're tailored to count data or microbiome data or trying to take into consideration some aspects of the data. So there are some limitations to these standard analysis approaches. First of all, if you use a classical statistical method, it actually does a pretty good job of protecting type 1 error in general, all right, when your sample size is large, as you would expect from central limit theorem and fun things like that. All right, and so here, if you apply linear regression, t-test, Wilcoxon test, other sorts of things that you learn in kindergarten, all right, they tend to work out. But as your elementary school teacher also taught you, all right, if you have zeros and ties, all right, you just don't do as well, all right? I had a CS person in my talk once, and he didn't learn until second grade. But, as statisticians, we all know this is just kindergarten stuff. And the issue, another issue here is it doesn't take full advantage of the data characteristics, and so oftentimes can lose quite a bit of power. So the type 1 error rate is great, but the power sometimes is fairly awful. The other approaches are tailored, are what I call the tailored approaches. And so these depend strongly on the normalization choices and the scale of your data. And so these can include approaches that were developed primarily for gene expression, so DE-seq2, for example, or there's something called metagenome-seq, which uses some degree of cumulative scaling, all right? But the problem here is that virtually most of these approaches tend to have relatively poor type 1 error control. Okay. And this is not something that we have observed. All right, there's a whole literature on the fact that most of these tailored approaches just do a fairly lousy job of protecting type 1 error. Right? And one of the major reasons for this is simply that the data don't follow the posited distributions. Right? DE-seq2, EDGAR assume a negative binomial, metagenome-seq assumes a zero-inflated log Gaussian or Gaussian, and then there's tons of other approaches that assume, gammas, betas, negative binomials, zero-inflated negative binomials, and all sorts of other things. When your sample size is modest, all right, you're never going to be able to detect deviations from these distributions, right? If you only have 3 points, you can basically tell me it follows any distribution, and I will have no evidence against that. But as your sample size gets much larger, modest deviations away from these distributional effects start really trickling into poor type 1 error control. right? So it really becomes an issue when your sample sizes are large over here. So this motivated our approach, which we called Zinc. And so Zinc is an approach where we do simultaneous conditional quantile inference for zero inflated abundance, all right? And so what we're doing is we're going to compare the distributions for say a bunch of controls and a bunch of cases over here, where C is some covariate of interest. Okay, it's a distribution test. Operationally, what we're going to do is we're going to summarize the difference at 0 counts and also at a grid of quantiles for the non-zero component, right? So you basically look at the 0 counts, and then we separate that from the positive part, and we look across a grid of quantiles there. In terms of the actual test for the non-zero component, we use a rank score-based test, which is computationally efficient, even for fairly large data sets. The main advantages of this, it tends to be robust in the sense that it doesn't make strong distributional assumptions, all right? It allows for covariate adjustment, and it allows us, because it's quantile-based, to detect heterogeneous effects across different quantiles in this case, all right? So we're again just using the same two-part model as before. So again, you use a logistic regression for the zero versus non-zero, all right? So these are a bunch of covariates. This is the variable of interest. And again, over here, for the non-zero components, over here, you again have dependence on covariates as well as your variable of interest over here, okay? And then to actually test the difference, what we do is we first test whether gamma from the logistic regression is equal to 0, all right? And whether all of these betas for given quantiles are equal to 0 as well, right? Against, the general alternative that there is something going on, right? So the testing strategy for the logistic component, you can basically do any test that you want. Your standard walled test, likelihood ratio test, score test. It's happy with anything over here for the most part. The quantile-based tests, what we do is on a grid of quantiles, we across the non-zero part, you basically get a p-value for each grid point, all right? The one thing you have to be aware of here, it's not just a standard quantile regression. You have to take into account the bias from the fact that you do have some degree of zero inflation. So the overall distribution now is squeezed over here because you have a bunch of zeros. Once you get a bunch of p-values, we combine the p-values from the logistic test and the individual quantile tests using either a minimum p-value strategy or a p-value averaging approach in this case. So here's the overall procedure. What we do is we take the outcomes over here, and then you basically pipe it into here, logistic regression for modeling the zero versus non-zero, and these conditional quantile regression models for the non-zero components. You get a single p-value from the logistic model, a bunch of p-values from the quantile approach across different grids, and then we either do a min p or a Cauchy combination test to get a single omnibus p-value for the association. Right? I'm not going to talk too much about these details. We're running out of time over here. There's a little bit of statistical messiness. The minimum p-value approach, we have to do some degree of resampling, which is why I tend to like the Cauchy combination test. It's just analytic and totally robust to correlation. I love that approach. It's made my life so much better. Okay, we're going to apply this to Cardia. The outcome in this case, so it's what we're looking at outcomes, and we're going to do associations between individualized normalized taxa, either rarefaction or cumulative sum scaling. Of course, Amy has shown very definitively, actually, that rarefaction is awful, but it is still what people use in the field, at least when we published this a few years ago. So covariates of interest, age, physical activity score, and dietary score were thought to be important, and so we adjusted for those guys. And again, the question is, which of these individual taxa has a distribution which is different between patients who are hypertensive and non-hypertensive? And we set the false discovery rate to 5%. All right, first, let's take a quick look at type 1 error control. This is just based on permuting the data. This is on count-based data, and this is on scaled data. And you can see that a lot of approaches that are tailored sometimes have somewhat inflated type 1 error issues. But if you look at some of the linear regression, for example, it does very well. Over here, these are the quantile-based approaches, right? And they seem to have pretty good type 1 error control on both rarefied as well as scaled data, right? So this is looking at power in this case. And so these are, again, the zinc approach, either using a min-P or a quotient combination or min-P. And so you can see the blue is the true positives in this case. And so it looks like it loses against some of these other approaches, but until you realize that these approaches can't control type 1 error and should never have been in this plot in the first place. Right? If you can't control type 1 error, then power is a meaningless concept in that case. All right, so we applied this to the Cardia data. And so these are the number of differentially abundant taxa by the approaches that seem to correctly control type 1 error in some cases. The ones with a star may have some degree of inflation. And so you can see over here that the zinc approach, despite actually having what we think is better type 1 error control, does seem to find more. And part of that is that it can actually identify taxa for which there are quite heterogeneous effects. So this is a Venn diagram of the numbers of taxa detected by each approach. So zinc is in the middle, the blue, and so you can see that linear regression, the linear decomposition model in Limma does find one more. QRank is another quantile-based approach, I think developed for, I don't remember what type of data, but it's another quantile-based approach, but doesn't deal with zero inflation. It finds one more, but most of those are all found by zinc as well. If you look on the cumulative sum squared scaling data, so this is now on a continuous scale, again, zinc finds most everything that everything else does. These linear approaches do find a few more, but overall there is pretty good overlap and we are finding a lot more things in general. Let's take a look at what we're actually finding. One of the things that we noticed was that zinc is actually able to do a pretty good job of identifying heterogeneous effects beyond just simple mean effects over here. So here is an example from rarefied data, and here's one on this for scaled data. This is Eubacterium over here. So the black line over here is the quantiles for patients who are hypertensive. The dashed black line is the mean value for the hypertensive patients. All right, the red is the quantiles for the non-hypertensives, and again, the red is the mean for the non-hypertensive patients over here. So you can see there is a fairly modest difference here in the means. All right, the difference is not very big, but if you start looking at the higher quantiles, you see that there's much more separability over here. And so this is a situation where zinc tends to do relatively well. If you look at just the median, there's nothing going on over here. All right, if you look at the means, relatively modest, but you can see that the scale of difference here is much, much larger. Now this is I'm sorry? The mean of the taxon abundance between hypertensive and non-hypertensive patients in this case.
Given that your relative abundance is sum to 1, isn't the mean the inverse of the diversity?
No, this is the mean for a single taxon in this case, right? The mean, in this case, we rarefied, and so it is the mean count in this case. Just taking a single taxon, and we're just, this is just on a single taxon basis. I'm sorry, I'm rushing a little bit, so sorry for being confusing. Yeah, so you see there's not much over here. This over here, again, quantile this is the distribution for the hypertensive patients. Over here, this is the mean for the hypertensive patients, quantile for the non-hypertensive patients, and the mean for the non-hypertensive patients for Haemophilus. And now this is an interesting one because you actually see crossing of the distributions over here. And what this means is that for these guys down here, all right, you actually see higher amounts for the patients who are non-hypertensive. But once you're talking about things over here, it flips all the way around. So you actually have heterogeneity in this over the distribution, right? And so if you look at it, if you just look at the means, they're basically identical, which is why you only see one line there. The medians also basically identical. So unless you look towards these non-central quantiles, you'll never be able to find this. And so we talked with our collaborators about this, or actually I think we gave a presentation somewhere. And then one of the microbiologists in the field, in the audience, told me that, hey, this makes perfect sense. Apparently Haemophilus is a very large genus, and it has a lot of members with varying and sometimes opposing directions of effect on various phenotypes. So they tell me it makes sense. I trust them. They could be wrong. I could be wrong, but that's the life of a statistician. I'm going to skip this and just say, in general, reliable testing of individual taxa continues to be a fairly challenging approach. So zinc is a quantile-based differential distribution test. We found that it tends to be robust to distributional issues and works pretty well under different normalizations over here. It tends to have better type 1 control than many tailored approaches, yet at the same time, still adapts to the characteristics of the data and so still seems to have reasonable power, particularly as it can capture heterogeneous effects over here. There are limitations, all right? It doesn't work well for low frequency taxa. And this is true for most of the approaches that we see. But here we're separately estimating the non-zero component. So we are particularly sensitive to that. It also doesn't work very well if the sample size is small. We tend towards conservatism. These are score tests. And so for whatever reason, they tend towards conservatism. But if we don't have enough data, we simply cannot estimate these distributions very well. And so we suffer again for that, right? But other than that, at least it seems to be reasonable. So just to acknowledge some people over here, much of this work was led by my former postdoc, Wodan Ling. She was a super minion who is now on the faculty at Cornell. And also my close statistical collaborator, Ni Zhao, is a faculty member at Johns Hopkins. So you should come here because she worked for me and not the other way around. So yeah, I'm trying to convince him to come here. So it's like, also you're less likely to get shot right outside of the building versus in Baltimore. There's a reason why they give you like a stipend for Uber. It's like really quite scary. All right, and of course, these are all my other statistical collaborators, the collaborators from who generated the data and my funding over here. And I'll stop here for any questions. And one of them can be why you should come here instead of Hopkins. Yeah, I think I've answered it many times. Yeah. Actually, I kind of like Baltimore, just scary. Huh? Oh, how do I, hi, Richard. Oh, do I have volume on?
Hi, Michael. Can you hear me?
I can hear you. I don't know if anybody else can hear you, but I'll repeat the question.
Oh, okay. I think it's really, really brilliant work. And I think I have a comment and a question about the first part of your work. The comment is, I think the way that you remove the batch effect by sort of imputing the distribution or the value, the corresponding cumulative probability is kind of the right idea in a causal modeling perspective, because in a way you're estimating a non-parametric structural equation model, and you sort of view this batch as a exogenous variable. And what you're actually doing is like imputing the variable under intervention where you set the exogenous batch variable to 0. So I think that makes a lot of sense. Then my question is, when you estimate different grids of quantiles, how would you ensure that they are monotone, they do not cross?
That's a really good question. So Richard asked about the quantile crossing problem. And the reality is here, we have not dealt with that. We basically have sort of swept that underneath the rug and we largely ignore that problem here. It is of concern, but we have not dealt with it in any way over here. So you're right. In some situations, you can have some degree of non-monotonicity in this case, but it still seems to work out. What we're actually working on now is instead of doing this quantile regression across a grid, we're actually doing a quantile process where you now treat it as this entire process. And in that situation, then you ensure the monotonicity and it no longer becomes a question. Very good question. You're right. We have not dealt with that.
So. Yeah. Okay, thanks. Very interesting. And I think it's also interesting to look at the quantile process proposal. I would be curious.
Yep, thanks. Other questions? No.
I guess you obviously you have to balance your model, so the batch can be different because of batch effect or also the variation studies.
Yep. Yeah. Yeah, so basically the issue that you're pointing out is that different covariate distributions are also different and perhaps correlated with batch. Is that the
I'm not sure about that.
yeah.
We're just looking at the difference. I mean, you could still see like some difference because maybe it's like summarized.
Yes, that is one of the possibilities that you still see some differences across batch because we've controlled for the covariate effect there. And if that's really where there's some differences, then that may still remain. Actually, one of the interesting things is that we thought that by doing this batch correction, our overall variability would be decreased, and we would actually be amplifying the signal of interest. But we actually don't see that very much here, which was kind of curious. And I think it is because of some degree of correlation among the covariates and also your batch variables. So
Signal probably stays, not the same, but the noise
that's what I thought, but the R squareds there, we're not seeing that pop out. And so we haven't done a careful investigation. Yeah. All right. Yep. Uh-oh, I'm in trouble now. Sure.
My question about the Kafka and Biostat aspect is maybe I'll need to hold the phrases, but I don't have a great sense of intuitively what the corrected distribution represents. So I guess I'm thinking about a situation where you've got different experimental protocols,
Mm-hmm. Yep.
and one you've got some taxa that are, or one taxon that's really easy to detect, and another you've got that same taxon much harder to detect.
Mm-hmm.
And then overlaid with that, you have differences in sequencing depth.
Mm-hmm.
And overlaid with that, again, you've got potentially heterogeneous. And I'm wondering, like, do you have a good sense of what your like corrected distribution?
Yeah. We've smushed everything together. And, there are, of course, severe limitations to that. And certainly, your work has highlighted a lot of the limitations of these types of approaches. But essentially, all we're saying is we believe that, these distributions and these effects are common across all of the batches. And so hence, if you had no variables or everything, then all of the distribution for these taxa would be identical across batch. So that is a fundamental assumption that you have to make. Yeah. Yes, we average over all of those things. It's not ideal, but in the absence of anything else that we can do right now, that's what we are operationally doing. But it's a good point. Those should be treated differently, but I'm not smart enough to know how yet. So, yeah. Mm-hmm.
Normalization, regression. My interpretation of the null hypothesis is that it's very strong. The quality of the entire distribution.
Yes, just like a Wilcoxon test. Yes.
But yes, I feel like in any conversation about Harrison's differential abundance methods, it's important to think about the fact that all of these many of these different methods that are
Mm-hmm. Yes. Very much so. Yeah. Well, I mean, I think at least here, I think that's a very, very interesting comment. And it's actually one that I periodically say, all of these methods test inherently different null hypotheses. And so you're absolutely right about that. When you put a parametric distribution on this, however, and you test those parameters, right? Like, for instance, if you do a Poisson, it's a single parameter model, then in fact, you are actually testing whether the entire distributions are the same in those situations, right? You're testing the Poisson parameter. The parameter indexes the entire distribution in this case. Okay, perhaps, but that's my view on that. But in terms of what we're operationally doing, we are operationally testing each of the hypotheses that each approach does and saying, hey, is it controlling the type 1 error under this very, very strong null that, that there's no difference across these? Because when we simulate these data, there's no difference whatsoever. So it should be under the complete null for every approach. So, yeah. Yeah.
So to kind of piggyback on that a little bit, right? So in the spirit of like a Wilcoxon test, like
Yep.
say you identify like here's a taxon,
Yep.
or here's a taxon that has the distribution differs.
Yep.
Right. A natural follow-up question is like, in what way does
Yep.
and obviously you can draw the plot.
Yep.
Right. But how confident are you in characterize, or is the appropriate thing to do like go get new data, do a more targeted analysis? And like say like, oh, like I think that the way they differ are in the tail. So I'm gonna.
As a statistician, the answer to that is yes. They should always get more data and do better. But the reality is, we just try to tease it apart as best we can. But that is a really good question. How do you characterize effect size for these things? And when you don't have these simple parameters here, it's difficult to say very much. All you're saying is that the distribution is different. And so that is a limitation of this as well. But, there's no free lunches, you got to make some trade-offs in this case. All right. All right. Yep. All right. Yep. Thanks very much. It's one of the, these things are very hairy, but I think Amy is right. There's a lot of much more complicated aspects of the data that we just haven't taken into consideration here. But in the absence of anything else, this is what we do. Like, I have to live in the real world. I got to analyze the data set in front of me because they pay me. But you're right. That is very much the case. So, yeah, thanks for coming. How are you doing? I haven't seen you in a while. I think I'm always over here and you're always over there. Yeah, thanks so much, Amy. Yeah. Oh, okay. But then I see you on the other side on Mondays and things, right? Yeah, thanks.